We'd like to thank Audible for supporting PBS. Quantum computing is cool, but you know what would be extra awesome? A quantum internet. In fact, if we want the first, we'll need the latter. And the first step to a quantum internet is quantum cryptography. Quantum theory may seem like an obscure subject of questionable relevance to the average person, but in fact, much of our technological world depends on our understanding of the quantum properties of the subatomic universe. And soon, perhaps very soon, we'll be interacting with the weirdness of quantum mechanics even more directly, with the coming of quantum computing and the quantum internet. Today, we're going to talk about the latter, specifically quantum cryptography and quantum key distribution, the foundations of the prospective quantum internet. We may come back to quantum computers in detail, but for now, just a word on why their advent will demand a quantum internet. The logic gates of a quantum computer exist in a state of quantum superposition of many simultaneous configurations. This allows the iterations of certain types of calculation to be done in parallel and vastly more quickly than a classical computer. For example, a quantum computer can calculate the prime factors of large numbers extremely quickly. This is bad because prime factoring is a cornerstone of internet cryptography. For the best description of classical internet cryptography on the internet, head to Infinite Series. By comparison, my summary will be pathetic, but here it is. To send encrypted emails or credit card details, two parties need to share a cryptographic key. This can be as simple as a number that you need in order to unscramble a message. The most secure way to do this would be to meet under a bridge on a rainy night and swap the key in advance, a so-called private key. That's impractical, so we use public keys. The most widespread example is the RSA protocol. Choose two prime numbers, one of which is very large, multiply them together to get an even larger number, and broadcast that as your public key. Anyone can then send you an encrypted message by scrambling the message with the public key using a special one-way function. It's a mathematical process that can't be undone with the public key, only with its prime factors, which only you have. All of this works as long as the public key can't be easily factorized back into its two primes. This is another type of one-way function. It's much harder to factorize large numbers than it is to create them by multiplication in the first place. At least as long as we're limited by classical computing. Once quantum computers can factorize public keys quickly, the entire public key system falls apart. There are two levels of snooping that encryption should prevent: simple eavesdropping and man-in-the-middle attacks. Eavesdropping is just someone reading some of your message data without you noticing. In an MITM attack, someone fully intercepts and controls a communication stream, essentially impersonating both parties to each other. The latter is especially dangerous because the attacker could potentially control the sharing of a public key, inserting their own key in the middle. Entire new levels of authentication are required to fix this. Of course, you could just meet under a bridge. A metaphorical quantum mechanical bridge, which allows the sharing of a secure private key. Enter quantum key distribution. This is a scheme to allow the generation of a shared private key, which can be used with a traditional encryption algorithm, or as a one-time pad which encrypts each message for a one-time use. While QKD doesn't really solve the authentication problem, it does make undetected eavesdropping impossible. QKD is actually two different schemes, at least that we'll look at today. Each highlights a different fundamental weirdness of quantum mechanics: the Heisenberg uncertainty principle and quantum entanglement. These will be the keys to unbreakable cryptography of the quantum internet. We'll start with Heisenberg, which of course we've done an episode on already. The uncertainty principle tells us that we cannot simultaneously know the values of certain pairs of properties. For example, a particle's position and momentum. These are so-called complementary or conjugate variables. Another example is the polarization of a photon, a quantum of electromagnetic wave. Polarization defines the direction that its electric and magnetic fields wave. You can either measure vertical versus horizontal polarization or diagonal versus other diagonal polarization. Rectilinear and diagonal polarization are complementary properties. Measure one perfectly and you lose all information about the other. An unmeasured photon exists in a state of maybe vertical, maybe horizontal, a superposition of the two, with maybe a preference for one or the other. It also exists in a superposition of diagonal states. You can measure the state by, for example, sending the photon through a polarizing filter. That act forced the photon to make a choice. First, which basis, rectilinear or diagonal, then which actual direction. So, for example, pass a randomly polarized photon through a horizontal polarization filter, like a polarized sunglasses lens, and the photon will either decide it's vertically polarized and be blocked, or horizontal and get through. Run that now horizontally polarized photon through a vertical filter and it'll be blocked because its vertical polarization component has been measured to be 0. In fact, here's a quantum experiment you can try at home. Try this with two polarized sunglasses lenses at 90 degrees. You'll see that all light gets blocked. Now, place a third lens in between at 45 degrees. Bizarrely, now some light gets through. What did you just do? Well, you just switched between different quantum representations of reality and then back again, and so invoked the uncertainty principle. See, any photon coming out of the first filter has its rectilinear polarization perfectly measured, which means its diagonal polarization is completely undefined. So when it then reaches that diagonal filter, it has a 50-50 chance of passing through. Then its diagonal polarization is perfectly defined, making its rectilinear polarization undefined, so it has a 50-50 chance to traverse that third vertical filter. This is the basis of one of the first quantum key distribution algorithms developed in 1984 by Bennett and Brassard and known as BB84. And no astromech droids were named after this key distribution protocol, which works like this. Imagine we have Albert and Niels, who want to decide on a private key for their messages, but they don't want to meet. Albert generates a random string of bits, zeros and ones, and encodes these bits using photons polarized in a particular basis, and uses a randomly chosen basis, either rectilinear or diagonal, for each of the photons. These bits are then sent over an open channel to Niels, who then randomly picks a basis of his own for each photon and projects onto that. If he uses the same basis that Albert did, he gets the same result, i.e. Albert sent a 1 and Niels also gets a 1. Otherwise, he gets a random result. Albert sends a 1, but Niels will get a 1 or a 0 with equal probability. Now, over the same public channel, they randomly pick a subset of those bits, and Albert reveals which basis was used for those photons and what he sent. If Niels uses a different basis, he ignores the result, because he knows it'll be random. If he uses the same basis, he should get the same answer. If he doesn't, he knows that something was up, and this is where the quantum part becomes useful. If someone, not Eve, Werner, intercepted these messages, which were after all sent on a public channel, and did his own measurements, he will have disturbed the system in a way that Albert and Niels could detect. That's because Werner, like Niels, can only pick a random basis each time on which to project the photons. If he picks the right one, the photon state is unchanged. Otherwise, it'll project the photon onto a random state, meaning that Niels isn't guaranteed to get the same answer as Albert, even though they know that they used the same basis. In this way, Albert and Niels can detect a man-in-the-middle attack. They would know that someone had knocked. Once they have done this test and verified that the information wasn't intercepted, they discard the non-matching measurements and keep the rest. Each translates to a bit, 1 or 0, depending on the basis choice, rectilinear or diagonal. This gives a number that becomes their private key, which now only they know. It's possible for Werner to get lucky and guess the exact same basis as Albert and so not disturb the state. But the chance is 1 in 2 to the power of the number of photons, which quickly gets close enough to impossible, given that Werner only gets one shot. This makes eavesdropping on the channel impossible. Man-in-the-middle attacks are in principle still possible because Werner could impersonate Albert and Niels from the very start. But there are classical authentication methods that can make this very difficult. So that's BB84, and it's one path to a secure quantum internet. Another way to generate secure keys using quantum mechanics was developed by Arthur Eckert in 1991. It uses a similar choice of quantum basis mechanism, but with the added frill of quantum entanglement. In fact, it looks for violations of Bell's inequality. Here, we definitely have to direct you to our full episode on quantum entanglement for the details. But the super brief summary: create a pair of particles with a quantum property that is correlated between the two. For example, electrons with opposite spin axes or photons with 90-degree polarizations. Our choice of measurement direction will set the direction for those spin or polarization axes. Here's where the entanglement comes in. Choose an axis or basis on which to measure one of those particles, say up-down for spin or rectilinear for polarization. And the other particle will also become measured in that basis. It will have the opposite when measured in the same basis. But even if measured in a different basis to its entangled partner, the results of those measurements will be correlated in a way that depends on the choice of measurement basis at both ends. This gives us another way to transmit a secure key. This time, Albert creates a set of entangled particle pairs and transmits one half of those to Niels. He then chooses a set of bases to measure his own particles. The choice of basis represents a set of bits. Niels chooses a random set of bases to measure the particles he receives. Because they're entangled, the outcome of Albert and Niels' measurements should be correlated in a very particular way defined by Bell's theorem. If not, then they know that the message was tampered with by someone, even if they can't say their name. But it was probably that Werner dude. He must have made some measurement and disentangled the particles en route. If Bell's theorem is satisfied, the entanglement must remain intact. No tampering occurred. Albert and Niels can create a private key based on the basis choices that happen to match, just like with BB84. For now, the classical internet is still moderately safe, or at least its biggest vulnerability is human stupidity, which, to be fair, will probably be the case with the quantum internet. But come quantum computers, even the smartest classical security protocols will be compromised. Then we'll also need a quantum internet, which we now know how to do in theory with quantum cryptography. But it's a different matter to actually build one. Quantum states, and particularly entangled states, are notoriously fragile, and so it's hard to transmit them across large distances. We'll show you how to construct a vast, planet-spanning network of encrypted quantum states real soon. Your browsing history may one day depend on it. And I assume that history isn't just old episodes of Spacetime.
We'd like to thank Audible for supporting PBS. Audible's selection of audiobooks includes Audible Originals, audio titles created by storytellers from around the literary world. For example, you can check out Bill Bryson's Science of Science, where Bill tells the story of scientific instruments that created the first map of Britain and the device that measures the temperature of the sea from space. It's an exciting narrative that explores the importance of collaboration in the field of scientific discovery. Visit audible.com/spacetime or text spacetime to 500 500 To learn more, members own their books and can access them anytime. To learn more, visit audible.com/spacetime or text spacetime to 500 500. Today we're covering comments from the last two videos, our episode on the galaxy without dark matter, and our coverage of the Event Horizon Telescope's black hole image. Let's get to it. Asplode asks about the interaction between dark matter and black holes. Do they interact? Can dark matter form a black hole? Well, assuming that dark matter is some sort of exotic particle, which is the going hypothesis, then black holes would definitely attract dark matter gravitationally and occasionally eat the stuff, but not too much of it. One of dark matter's defining qualities is that it doesn't clump together. It remains diffusely spread out through our galaxy. Occasional dark matter particles would be snared by black holes and they would add to the black hole's mass just like regular matter. But dark matter alone could never clump together densely enough to produce a black hole by itself. Munray asks whether putting radio telescopes around the sun would improve the resolution of an interferometer. Hell yeah, it would. The minimum resolvable distance is inversely proportional to the separation of the antennas. Tommy Barlow states that neither the event horizon nor anything near it was imaged. Yeah, that's right. The event horizon is invisible, but the telescope did resolve down to the size of the event horizon. What was imaged was light escaping from the photon sphere that was produced in a magnetically driven jet. That's probably around 5 times larger than the event horizon in the case of this quasar. But seriously, the light from outside the event horizon, because we can't actually see the event horizon telescope, doesn't have such a nice ring to it. The Inebriati logs the following. Day 37,736, Einstein still appears to be right about general relativity. I know, right? At this point, do we just give up trying to disprove the old man and just settle for the fact that it's probably all right? Answer: never. That's not how science works. Still, nice run, Albert. Belodri writes from Austria to inform us that their phone ring is now me saying Zwicky. Belodri, please notify us if you're ever coming to New York so that I can not leave the house. Randomly hearing that while walking down the street would creep me out too much.